So again, practicing the concepts conceptually. So more practice with conceptual understanding of force and motion. There's going to be 3 examples in this video. I'm just splitting into multiple videos to keep the videos shorter. So let's go ahead and look at this question. Pause and decide on your answer, please. All right, so practicing, I'm still going to draw free body diagrams simply because I'm asking you to do so when you get to your test. So it's really good to keep practicing. We have a cart, so this dot I have drawn represents the cart. It's moving, it's on a horizontal frictionless table. Once the cart has been given a push and released, so we know the cart itself is moving to the right. It has a velocity to the right. We want to know what's going to happen to the cart. And we're assuming it's staying on this horizontal frictionless table because they don't have any other information they've given us. So let's consider the forces acting on the cart in terms of the free body diagram. We, of course, know there's the force of gravity. We can't get rid of that. When we're on the Earth is always pulling objects towards the center. So that's our field force. This cart itself is in contact with the table. So there has to be a normal force. That normal force is perpendicular to the table, so it points straight upwards. The problem tells us that there is no friction, so I don't draw friction in there. We will continue to ignore air resistance of any sort for now. So the free body diagram of this particular cart is simply this normal force up and the force of gravity down. Since the cart is moving on the horizontal table, just commonsensically, if we rolled something across the floor, the horizontal floor, in terms of up and down motion, the y direction, we know the normal force needs to cancel out mg. Otherwise, there would be acceleration in the y direction. So this cart would have to be like a rocket ship and start taking off upwards or downwards. It could sink, in theory. But of course, we know that's not happening. It just continues moving horizontally. That tells me that the normal force needs to balance out mg in the y direction, because there's no acceleration in the y direction. In the x direction, there's no forces for this x direction at all. If there's no forces, then according to Newton's second law, there can be no acceleration in the x direction. So if there's no acceleration, our cart it's been pushed, but we're no longer pushing. The problem specifies it has been released. This cart is moving such that its acceleration is 0. That means its velocity will not change. So it cannot come to a stop. There'd have to be friction to stop it, or some other force to stop it. Technically, it's going to continue with an acceleration of 0. So that is constant, but that is only one example of a constant acceleration. When we say continue with a constant acceleration, we imply just a constant number, not necessarily 0. So B is not the answer. We know the acceleration is 0, so it's certainly not decreasing. It's not stopping because there's no acceleration. Its velocity has to change. Now we could, of course, have read through all these options and jumped to D first. No acceleration means the velocity is not going to change. That means it is constant. So D is correct here. All right, one more example. Well, and then another one. I said I'll do 3. So here's our second question. Please pause, decide what you think the answer is. All right, the ball. Viewed from above, as the ball continues through this tube, there's a force from the wall of the tube. So the ball continues moving, but the wall of the tube is in the way. There's a net force. There's a force from the wall pointing towards the center because the tube is in a circle or 3/4 of a circle. So at this moment, right before the ball leaves, there's still this force towards the center. But right now, as it comes out, there's no force towards the center anymore. If there's no force towards the center anymore, there's nothing to make it turn. So it's just going to move it with a constant velocity. Same speed, straight line in that direction it had the instant it comes out. So because of how the tube is oriented, that moment that the ball comes out, it is headed directly in that direction of C. And so that will be the direction it maintains. There has to be a net force to make the velocity change. So options A and B both represent a change in velocity because the direction would be changing. There would have to be a force that was making that happen, which is not the case here. The tube's gone. Friction, in the case of a ball rolling through, is not going to cause that to happen. So C is the correct answer. This gets back to Newton's first law, the law of inertia. Object moving is going to continue moving if there's no net force action on it. So it continues moving with a constant velocity. We are going to talk about circular motion like this in chapter 8, in a couple chapters. The nice thing is Newton's second law still totally applies. There's an acceleration because the velocity is continually changing direction. If there's an acceleration, then there must be a net force causing that acceleration. So we'll talk about that later. One more example for this video. Here's the last example in this particular video. Go ahead and pause. Decide your answer. Okay, I'm going to start with the free body diagram before answering the question. I just want to recognize what forces are acting. This object, whatever this guy represents here, we know, of course, there's a force of gravity. That's our field force. We can't turn off gravity. The other thing in contact with this object is the rope. Ropes can only pull, and they pull along the length of the rope. So I would draw tension along that length. Now, I'm not thinking about the length of it at the moment. I just want to recognize what forces are acting. In terms of this question, they want to know, they're asking us to compare tension and weight. Remember mg, force of gravity, we can also refer to as weight. So they're essentially asking us which of those two forces is bigger. To reason through that portion, we need to come back to the problem and look at what it tells us about the motion. So we're told this object is being lowered. So the velocity, it's drawn on the picture right here. If the object's being lowered, then its velocity points downwards. The acceleration, we have to reason through that like we did in the previous section. It tells us in the problem that the speed is steadily decreasing. So this object is slowing down. If the object is slowing down, then there must be some sort of acceleration in the opposite direction to make that object slow down. So this is from our previous section. Opposite directions mean slowing down. The new stuff here is that the acceleration of an object is determined by the net force and then the mass. The direction of the acceleration is up. That means the net force must be up. The acceleration always has the same direction as the net force. So coming back to our free body diagram, in order to add these two forces together and get an answer that points upwards, tension has to be bigger than mg, or weight. That rope has to pull harder than the force of gravity to slow that object down and stop it. So let's see, the rope tension is greater than the object's weight. So that is option A. This reasoning process is very helpful when we solve problems.